Good evening, everybody. Welcome to Chem 1211 with your host, me, Dr. White. Hi. Tonight I'll be doing the review for test number 1. Now let me open up something on Blackboard. All right. Let me remind everybody, test number 1 will be given from the 15th of this month through the 19th. That's this Saturday and next Monday, Tuesday, and Wednesday. And you have to take test number 1 at the Glen Ellen Testing Center, and that's on the main campus. Look at their webpage for their hours on Saturday and also Monday through Wednesday. Now, test 1 will cover chapters 5 through 10. It'll cover chemical bonding. Let me move this out of the way, including ionic covalent chemical bonds. It will cover mole and mole-related topics, including balanced chemical equation. There are 4 problems on balanced chemical equations. Oops, I shouldn't have said that. Yes, I said. All right. There'll be 21 problems on 9 pages. There's no multiple choice, but some questions are multiple part. And when we break down the topic area, chemical bonds and related topics like valence electrons, things like that, 44 points. Mole and mole-related topics, including balanced chemical equations, 56, and it adds up to 100. Now, under your name on test 1, it will say, please use proper significant figures for all calculated answers, and it will say, please use 3 significant figures for all atomic masses. Now, let me tell you about the testing center. I have given everybody, because it's sometimes distracting being in there, 2 hours. If we were face-to-face, you would have 55 minutes. And this test would take about 45 minutes, maybe 50 minutes. Everybody should have enough time if we were face-to-face, 55 minutes, an hour, maybe to finish. My tests are written such if you've done the practice problems, hint, if you've done the practice problems, you should have plenty of time to finish the test. But I'm going to give you 2 hours. What that means is you've got to get to the testing center more than 2 hours before they close. Because I put down a 2-hour max window. You can leave early if you finish early. If you get there later in the day when there's not 2 hours from the time you start to finish, they will not let you take the test. You'll have to come back another day. So I highly recommend, 1, you come in the morning if you can on Saturday, Monday, Tuesday, or Wednesday. I try and go Monday or Tuesday. Next, you can only have scientific calculators. They have the ones they'll lend you, but if you're not used to theirs, that makes life challenging. Bring your own calculator. It can't be the kind with the graphing and the big window, but a regular scientific calculator, bring it. You'll need a photo ID. And also, I'd bring a writing implement. Hint, I would bring a pencils and a good eraser. Now, what I like to do is go through test 1 review. This one was originally written for fall 2022. Well, that's a while ago. But anyways, it's still valid. This is located, what I'm showing you, in the lecture section of D2L. Wrong school, Blackboard, sorry. All right, when we talk about electrons, remember in the center of the atom are the protons and neutrons. Where are the electrons? They're in the electron shells that surround the nucleus. But it's not like the planets around the sun. It's a little more complex. Now, electrons occupy what's called electron shells. Now, one thing I should mention, and if you've watched the videos, which I hope you have, you've seen me talk about important information test one. Now, up until last semester, I would include this with test one. Last semester, department chairman made a ruling. Faculty, meaning me and other faculty, can no longer put this type of information at the end of a test. So I have to follow the rules because I do. And therefore, this is stuff you need to memorize. I'll say that again. This file is also in Blackboard in the lecture section, cleverly named Chem 1211 Test 1 Important Information Fall 2022. It's still valid now. Like I said, you will need to memorize this. In the past, I gave all this to you being the students, but this is important. There's other things you need to memorize, but clearly you need to know the information on these two tables because I no longer can do what I used to do. Sorry, but I have to follow rules. All right, so where are the electrons? They're in the electron shells. And you should know the shells have very fancy names, shell 1, 2, 3, 4. And you should know the number of subshells. Shell 1 has one subshell, 2, 2, 3, 3, 4, 4. And you should also know, I got to take the cover off my stylus so it will work. Yep, it's working now. That shell 1 is the lowest energy. And as you go down, the energy of the shells increase, and shell 4 is the highest energy. And when you're putting electrons in the shells, you always fill the lowest level first. Now, the shells have subshells, and they're lettered S, P, D, and F. That's the names. And I don't have it on here, but I go in, it's the names, what S, P, D, and F stand for. But anyways, S is the lowest energy, then P, then D, F is the highest. I have it here. Now, when we talk about the subshells, how many electrons, what's the maximum? And this really should read maximum number of electrons you can put in that subshell. S is 2, P is 6, D is 10, F is 14. Now, for my test, you just have to know S and P. Because in the videos, you heard me give a gift to you. And for test 1, you'll need to know the elements from hydrogen through magnesium, when we do something called the electron configuration. Again, those are the only ones for test one, hydrogen through magnesium. That's my gift to you. Thank you, Dr. White. You're welcome. So these are the subshells, S and P, and that's 2 max in S electrons, 6 in P. Now, when we talk about electrons and where they are in an atom of an element, we talk about the electron configuration. That's the statement, how many electrons an atom has in its subshells. And the way to remember that is it's numbers, letters, then superscript, that means higher, up or above, superscript numbers. So let me open up something. If I were to ask you, draw the electron configuration of nitrogen, how do you know how to draw the electron or write the electron configuration of nitrogen? Well, first of all, you have to find how many electrons there are. And you go to the periodic table. And for nitrogen, you look at the atomic number, and that gives you the number of electrons. Nitrogen has 7. So we have 7 electrons. Now, the first shell is 1, the lowest energy. 1 has only one subshell, and the lowest energy subshell is S. And you can put 2 electrons max in S. So we have 2S, or 2 electrons in 1S. Well, we still have 5 to go. Now, 1 has only one subshell, 1S, and we filled it. So we go to the next lowest energy shell. That's 2. And the lowest energy subshell is 2S. Remember, a subshell is identified by a number and a letter. I'll say that again in slow motion. A subshell is identified by a number and a letter. Well, how many electrons can I put in 2s? Well, any s orbital, the answer is 2. Well, I filled that up. Well, I've got 4 electrons, but 7 minus 4 is 3, so I got 3 more to go. Now, S has 2 subshells. The lowest energy is 2s. The next lowest, which is the second one, is 2p. Now, I have 7 minus 4. Where did I get the 4? 2 plus 2. And that means I have 3 more to go, electrons. Now, P, you can put a maximum of 6. Well, I only need 3, so I can do that, and I'm done. And the electron configuration for nitrogen is 1s2, 2s2, 2p3, 7 electrons. Let me get rid of this. I keep on looking at that where I want to go to the review. All right, next thing are valence electrons. And you should know the valence electrons are the outermost electrons of an element. Again, you should know that the valence electrons are the outermost electrons of an element. And the number of valence electrons for an element can be found on top of the column of the periodic table. So let's look at a periodic table. This is the periodic table you'll be given for test number 1 at the testing center. Probably won't be on green paper, even though St. Patrick's Day is coming up. But the number in red here at the very top tells you how many valence electrons each element in that column has. Hydrogen has 1, lithium 1, sodium, magnesium 2, carbon 4, nitrogen 5, chlorine 7. And if we look at the noble gases, krypton and argon have 8 valence electrons, so does helium, neon, and xenon. So the number on top gives you the number of valence electrons. Now, to show the valence electrons of an element, we use the Lewis structure. And the Lewis structure uses the chemical symbol. And when you talk about a Lewis structure, you're only talking about the valence electrons. And when you draw a Lewis structure, you put 1 valence electron on each side of the chemical symbol before doubling up. So if I were to ask you to draw the Lewis structure of iodine, which has the chemical symbol I, you'd have to go to your friendly neighborhood periodic table, say iodine right here, a halogen has 7 valence electrons. So I'm going to put 1 on each side, a dot for each valence electron, and now I can start doubling up. And notice iodine has 7 valence electrons. There's 7 dots. You could have also drawn it this way. And there are 2 other ways. 3 sides has 2 dots. 1 side has 1. And that's the valence electrons. Now, how do atoms come together to make molecules? By a chemical bond. There are 2 types of chemical bonds, ionic bond and covalent. You should know that an ionic bond results from the transfer of 1 or more electrons from one atom or group of atoms to another atom or group of atoms. Again, you should know an ionic bond results from the transfer of 1 or more electrons from one atom or group of atoms to another atom or group of atoms. Now, a covalent bond results from the sharing of 1 or more pairs of electrons between atoms. Again, a covalent bond, and you should know, hint, results from the sharing of 1 or more pairs of electrons between atoms. Remember, a pair means 2. Now, I'll never ask you what the octet rule is, but in compound formation, when you're bringing atoms together to form molecules, atoms of elements lose, gain, or share electrons in such a way that their configuration becomes identical to that of the nearest noble gas in the periodic table. And that's 8 valence electrons. Now, I expect you to know how to determine what's the charge on an ion, what ion the elements form. And you use the concept, elements lose or gain electrons that have the same number of electrons as the nearest noble gas. Nearest meaning nearest numerically, the number of electrons to the nearest one. So if I were asked on test one, what ion does calcium form? Calcium is Ca. Now you need to go to your friendly neighborhood periodic table, and here it is. And calcium is at 20. That tells you you have 20 electrons and 20 protons. Now, you could say, what are the nearest noble gases? Argon at 18, krypton at 36. Now, krypton is 16 away. Argon is only 2 away, numerically looking at the atomic number. I see a question. Sometimes if I missed you, question was asked, is the use of a periodic table allowed during test one at the center? Yes. You will be given a copy of this periodic table along with your test, and it just won't be on green paper. The year I scanned this, the copy center did it on green paper. I don't know why, but they did. Well, I do know why. But anyways, you'll be given a periodic table. I do not expect you to memorize atomic numbers or atomic weights. All right, so argon is only 18 away. Remember, the atomic number is the number of electrons and protons. Now, calcium starts with 20 electrons, 20 protons. It wants to have the same number of electrons as mental break, argon at 18, but it will still have its 20 protons. Each electron has a -1 charge. Each proton has a +1. -1 times 18 is -18. +1 times 20 is +20. Add them together, +2. And when I ask what ion does calcium form, you show it by the symbol and superscript to the right, whether it's plus or minus, in this case it's plus, and the number 2. Now you can write it the old way, which Dr. White likes to do it, or the newer way, putting the 2 before the plus, either one. Now, for ionic compounds, all molecules have a net 0 charge. And therefore, the number and kind of ions that make up the ionic compound, it has to add up to 0. So if I were to ask you, draw the simplest formula or the empirical formula for a molecule with calcium +2 and iodine -1, this has to add up to 0. So this is a +2, this is a -1, and it has to add up to 0. Well, it doesn't. You cannot change the charge. You can't. But you can change how many. And if I put a 2 there, now this is +2. 2 times -2 is -2, and it adds up to 0. And what does that tell me? The formula for a molecule, the simplest formula for a molecule with calcium and iodine would be a calcium 1 and 2 iodine, and that would be it. Now, for polyatomic ions, now let me change this. There, that's what I like. Again, the question would be, write the simplest formula, or I might use write the empirical formula for the molecule, ionic molecule with magnesium and nitrate polyatomic ions. Well, this is a +2. This is a -1. All molecules have a net zero charge, so they have to add up to 0. Oh, no, it doesn't. Well, you can't change the charge, but you could change how many. And now this is a +2. 2 times -1 is a -2. It adds up to 0. What this tells us is there's 1 magnesium and 2 nitrate. Now, for a polyatomic ion, you use a bracket when you have more than one, write the ion, and then close bracket and subscript, how many of them are there? In this case, 2. And that's how you do it. Now, when we talk about molecular compounds or compounds with covalent bonds, those are where they share valence electrons. And there's bonded electrons, those involved in a bond, and non-bonding electrons, those that are not involved in the chemical bond or sharing. Now, it's time for Dr. White to get subtle. And know this, there are 3 types of covalent bonds. And they are the single bond, double bond, triple bond. A single bond is where, and you should know this also, 2 atoms share 1 pair of electrons. A double bond is where 2 pairs of electrons are being shared. And a triple bond are where 3 pairs of electrons are being shared. Now, if I were to ask you to draw the Lewis structure for nitrogen gas, N2, 80% of what you're breathing in now is that gas, what is the Lewis structure? Well, you go and find how many valence electrons nitrogen has. And here we look at the periodic table, not the atomic number. The number on top, 5, tells you it has 5 valence electrons. So nitrogen has 5 valence electrons. And we've got 2 of them. And if I draw the Lewis structure for each element, it looks like this. And nitrogen here says, hey, I've got 3 unshared electrons. And this nitrogen says, I do too. Let's share pairs of electrons. And the non-bonding electrons on the top, they don't share. So 3 pairs. And this would be the Lewis structure for nitrogen gas. And what kind of bond is between the 2 nitrogens? 3 pairs. That's a triple bond. Now, one thing you should know, you can have molecules with both ionic and covalent bonds. And let's look at one. Sodium hydroxide. Now, whenever you see an alkali metal, it's always going to be an ion. I know of no example where you have an alkali metal as in a covalent bond. What ion does sodium form? This one. And we went through that in the videos. Now, sodium has one valence electron. Oxygen has 6 valence electrons. And hydrogen has one valence electron. Now, oxygen has 6 valence electrons. Hydrogen has one, and they share. But remember the octet rule. The one exception is the octet for hydrogen is 2. The one exception to the octet rule is that hydrogen has only 2 valence electrons. Now, if we look at oxygen here, shared and unshared, it's got 7. Oh no, what do we do? Well, remember, sodium had one valence electron, but to go to the ion, it gave it up. And where did it go to? Right here. So now this has an extra electron and a negative charge. And that's the Lewis structure for sodium hydroxide. There's an ionic bond between the sodium and the hydroxide, polyatomic ion, and there's a covalent bond between the oxygen and hydrogen. Remember, water is covalent. Just remember, sodium chloride is ionic. Anything with an alkali metal is always going to be ionic or have ionic bonds in it. All right. Now, one thing I should mention, this is a review. Go back and work the practice problems. Just like you found in quiz 1 and 2, there's a reason I call them practice problems. And you'll find out after test 1 why I call them practice problems. Now, when we talk about molecules and even atoms, they're tiny, real tiny, and they're much tinier than that. And to understand and grasp them, chemists came up with the concept of moles. You should know, what is a mole? A mole is a chemist's counting unit. Now, there are important relationships between moles of an element and atoms, moles of a compound, and molecules. And that is, and this should be, sorry about that, sports fans. One mole of an element equals 6.02 times 10 to the 23rd atoms of that element. And one mole of a compound equals 6.02 times 10 to the 23rd molecules of the compound. 6.02 times 10 to the 23rd is called Avogadro's number, in honor of Avogadro, a great Italian scientist who helped advance the concept of moles. He didn't come up with that number, 2 German chemists did, but they named it after him. You should also know 1 mole of an element equals the atomic weight of that element in grams, and 1 mole of a compound equals the molecular weight of that compound in grams. And finally, the molecular weight of a compound is the sum of all atomic weights. Bear with me while I'm opening up some files. Now, if you notice down at the bottom, it says use your good buddy, your good friend, unit analysis. And hopefully you've been watching the videos and practicing the practice problems. But let's look at an example. Remember, 1 mole of a compound equals Avogadro's number, 6.02 times 10 to the 23rd molecule of that compound. So and let's look at let me make sure you can see it and the answers you can. And you should know how to be able to do the following word problem. Relax, take a deep breath, let it out. And the first thing you should do is ask yourself, what are we being asked to find? Now, the question is, how many moles of water are 3.11 times 10 to the 29th molecules of water? So we're trying to find moles of water. We're given 3.11 times 10 to the 29th molecules of water. Well, the only thing we really have to start with is this. So I'm going to put it down here. By the way, it pays to show your work on my test. You'll be given a paper to write the answers down. Actually, the questions will be there too. Just like my quizzes, show your work. If you make a math error, I'll only take off 1 point. If you put down an answer that's wrong and don't show your work, you'll get 0 points. Now, if there is some magic ratio that I multiply this number by, what units do I want my answer to be in? And the answer to that question is right there. We are trying to find moles of water. And now it's time to use your good buddy, your good friend, unit analysis. I hope Zoom didn't blank that out. Whatever units you're trying to get to, goes on top of the ratio. Whatever units you're trying to get rid of, go underneath. I forgot to write here water. So let's write that in. I want to get to moles of water, and I want to get rid of, and so I put it on the bottom, molecules of water. And the important thing with unit analysis, whenever you have two things equal, A equals B, there are two ratios you can write, A over B, and not equal, but two separate ratios, B over A. Now, where do we know something about molecules of water, which is a compound, and moles of water, which is a compound? And hopefully you've memorized 1 mole of a compound, water, equals Avogadro's number in molecules of that compound. So A equals B, 1 mole of a compound equals Avogadro's number. So remember, 1 mole of a compound, in this case water, equals Avogadro's number when two things are equal, two ratios, 1 over Avogadro's number, 6.02 times 10 to the 23rd. Now, before you pick up your calculator, notice up above here we have molecules of water, and it's divided by the units molecules of water. Anything divided by itself equals the number 1, meaning this cancels out. And we're left with this units moles of water, which is what we're trying to get to. And now I can happily pick up my, oh, that was bad, sorry. My calculator, put 3.11, remember, second key, double E, 29 divided by 6.02. Remember, on this calculator, second key, double E, 23. And my calculator gives me this number. Now, as I said earlier, on test 1, please use proper significant figures for all calculated answers. And therefore, for multiplication and division, you get the same number of significant figures as the number that has the fewest significant figures that you're multiplying and dividing by. This is 3 significant figures, 6.02, 3 significant figures, and the 1 is an exact number, part definition, and therefore plays no role. And therefore, the lowest number, 3 and 3, is 3. So you have to round this off to 3 significant figures. Keep the 5, keep the 1, keep the 6. Use this to round off. It's 5 or higher. Increase that by 1. And the proper answer here, 5.17 times 10 to the 5th moles of water. And that's how you do unit analysis. And it will be your good buddy, your good friend. Now, if we look at this relationships, 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound equals the sum of all atomic weights. And now, I'm going to take a drink of water. Hold on, time out for a water break. Oh, my throat needed that. Thank you. All right, now the first thing is for the problems on some of the problems on test 1, you have to know how to determine the molecular weight. And the molecular weight, which I abbreviate MW, is the sum of all atomic weights. And the molecular weight of water, you have 2 hydrogens, 1 oxygen. Now, remember on test 1, it will say underneath your name, please use all atomic weights to 3 significant figures, rounded off. And if we look at, oops, I don't have to do that. If we look at our periodic table, for hydrogen, 1.008 rounds off to 1.01 for 3 significant figures. For oxygen, 15.999, the atomic weight is the number underneath the symbol, chemical symbol. Remember, you will be given this periodic table, so you'll be familiar what it looks like. And 15.999 round off to 3 significant figures, 16.0. So you have 2 hydrogens, 1 oxygen. Each hydrogen is 101. Each oxygen is 16.0. Do the math. Now you add it up. Now, listen carefully. Unlike multiplication division, you get the same number of significant figures to the right of the decimal as the number to the right of the decimal you're adding that has the fewest significant figures. And any number including 0 after the decimal is significant. So if we look at here, 2.02 has 2 significant, 16.0 has 1 significant. The number, when you add it up, everything to the left of the decimal, you just add up and leave as is. This is 0.2, and you round that off to 1 significant figure to the right of the decimal. Keep the 0, use the 2 to round off, that's 4 or less, and drop it. And the correct answer for the molecular weight of water is 18.0. And similar to the other ones. Now, let's look at number 15. How many moles are 34.56 grams of water? We're trying to get moles of water. We're given grams of water. The only thing we have to start out with is this number. And we're trying to get the moles of water. So now if you have a ratio that will convert this to moles of water, use your good buddy, your good friend, unit analysis. You have a ratio, moles of water go on top, grams go underneath. And where do you get this? 1 mole of a compound equals the molecular weight of that compound in grams. So 1 mole equals the molecular weight. Now here I have, again, we just did it, the molecular weight of water is 18.0. So 1 mole is 18.0. And use the grams for this, and the moles is 1 mole. And now you do the math, 4 significant figures, 3, the 1 is exact, and the number you get is a 3 significant figures. All right, now on test 1, there'll be 4 balanced equations, and I went through in the video. Remember, when you balance an equation, you have the same number and the same type of elements on each side of the arrow. Remember, at the base of the arrow are the reactants. At the head of the arrow are the starting materials. Are the products. Been a long evening already. I'll say that again. Base of this arrow, reactants, it's also known as starting materials, head of the arrow, products. And notice here, you can't change the formula, but you can change the number in front called the coefficient. And for one, well, if I have 2 chlorine here, how do I get 2 chlorine there? Put a 2. Now I'm going to have 2 sodium, so I put a 2 there. Now, remember my advice for balancing chemical equations. Leave hydrogen, oxygen last. Leave hydrogen and oxygen last. Balance all the other elements and then do those. Makes your life a lot easier and successful. For even odd, watch the video on balancing chemical equations to see how to do that. Now, there are 2 very important types of calculations you will need how to do for test number 1. And here, I should have shown you this for a chemical equation. A and B are the reactants, C is the product. Here's tips on how to balance it. Now, there's an important 10-point problem, called mass calculation for reactions. And you got to do 3 separate steps. The first one is convert mass of A to moles of A. Second step, moles of A to moles of B. And the third step, moles of B to mass of B. And this is real world. I had to do calculations like this when I was in the chemical industry, where hundreds of thousands of dollars was on the line. You don't make mistakes then. I never did, at least, thank God. Not to bring religion into the classroom. Now, if we look at, first of all, let's do something simple. For the following reaction, how many moles of oxygen are needed to make 23.33 moles of CO2? This would be like step 2 of what I just showed you. You want to find moles of oxygen, and you're given moles of carbon dioxide. So you start with this. You want to get the moles of oxygen. If you had a ratio to convert this, use your good buddy, your good friend, unit analysis. Whatever units you're trying to get to, go on top. Whatever units you're trying to get rid of, go underneath. And where do you get a relationship between moles of oxygen and moles of CO2? From the balanced chemical equation, which I'll always give you. When there's no number in front, like in front of C3H8, it's the number 1. And the coefficients, the number in front, give molar relationships. So this tells you 1 mole of C3H8 reacts with 5 moles of oxygen to make 3 moles of CO2 and 4 moles of water. This is one of the most powerful concepts in all of chemistry. And therefore, where do we get the relationship between moles of oxygen, moles of CO2, carbon dioxide? Right here. For every 5 moles of oxygen, you make 3 moles of CO2. These numbers are exact numbers. I made a mistake here. This should be 4 significant figures, but it's only 3, and you do the math. On this one, I got it right, 3 and 3. All right, now, let's look at number 4, 10 points. For the following reaction, H2 plus Cl2 makes 2HCl. How many grams of hydrogen are needed to make 125.6 grams of HCl? You'll learn way later in the semester, HCl is hydrochloric acid. That's the acid in your stomach that helps break down food. And it's also used industrially in many things. All right, so what are we trying to find? grams of H2, hydrogen gas. We're given grams of HCl. This is the one where you need 3 steps. The first step, whatever you're given the weight of, you have to convert that to moles. The first step, whatever you're given the weight of, you have to convert that to moles. So you have the weight of HCl. You want to go to moles of HCl. You have a ratio. Whatever you're trying to get to goes on top of the ratio, moles of HCl. Whatever you're trying to get rid of goes underneath, grams of HCl. Remember, 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound in grams is the sum of all atomic weights. So 1 mole of HCl, here you have to calculate for grams of HCl the molecular weight. And that's 1 hydrogen, 1 chlorine, and that's 36.5. Do the math, and you get 33.44 moles of HCl. Now, second step, you go from moles of whatever you just calculated, in this case, A is HCl, to moles of what you're trying to find, eventually hydrogen. So you have a ratio. Whatever you're trying to get to goes on top of the ratio, moles of H2. Whatever I'm trying to get rid of goes underneath, moles of HCl. Where do I get this relationship of moles of a compound and moles of another? From the balanced chemical equation. Remember the coefficients. When you don't see one, it's number 1. So this balanced chemical equation tells me 1 mole of hydrogen reacts with 1 mole of chlorine to make 2 moles of hydrochloric acid, HCl. So every 1 mole of hydrogen reacts with 2 moles of HCl. These are exact number, 3 significant figures. You get this number. Are we done? No, we want to get grams of hydrogen. So now you need the third step. Third step is convert moles of B, in this case hydrogen, to mass of B. And once again, we'll use these 2 statements. 1 mole of a compound equals the molecular weight of that compound in gram, and the molecular weight, and let me get this out of the way, molecular weight of the compound is the sum of all atomic weights. So we have 1 mole of hydrogen, or moles of hydrogen. We want to go to grams of hydrogen. Again, you have this ratio. Use your good buddy, your good friend, whatever I'm trying to get to, grams of hydrogen go on top. Whatever I'm trying to get rid of, moles of hydrogen, go underneath. 1 mole of hydrogen equal the molecular weight of hydrogen. The molecular weight of hydrogen is the sum of all atomic weights. There are 2 hydrogens in H2. Each hydrogen has atomic weight of 101. Therefore, that's 202. You go and do the multiplication, round it off to 3 significant figures. Now, notice here I have 3.47 or 3.48. Now, there's 2 philosophies. Time out for a water break. This is thirsty work. Now, there are 2 philosophies when you have multiple step calculations like this on how to round off. One philosophy is round off at each step. The other is round off at the very end. I'm a round off at each step person. Now, I'm not going to force you to do my way, but I calculate both ways. Sometimes they're the same answer, sometimes they're slightly different, and you can do it either way. And that's how you do mass calculations for reactions. And if you look at the problem set, I have a couple others, plus I have in my videos, obviously, where I go through that. And remember, the coefficients of a balanced chemical equation are molar ratios. And finally, the last thing of test number one is called limiting reactants. And this determines the number of moles of a product produced using each mole of the reactant. And the lowest number is the answer. That's when you don't have enough of one chemical and you want to see how much am I going to make total. All right, let's look at number 8. For the following reaction, how many moles of water, and you should know water is H2O by now, are made when you react 4.12 moles of C3H8, that's called propane, that's stuff in the white tanks for your barbecue, with 18.4 moles of oxygen. And you need 2 steps. The 2 steps are, for each reactant, you calculate how many moles of the product you're going to make. And therefore, the lower number is the answer. So we're trying to find how many moles of water. We're given 4.12 moles of C3H8 and 18.4 moles of O2, oxygen gas. So the first calculation or step is I take the first reactant, in this case C3H8 propane. I have 4.12 moles of that, and I want to find out how many moles of water will I make. Well, here's the moles of water. If I had a ratio, I use my good buddy, my good friend, unit analysis. Whatever we're trying to get to goes on top, moles of water. Whatever we're trying to get rid of goes underneath, moles of C3H8. Where do I get these numbers? From the coefficients of a balanced chemical equation, give you molar relationships. When there's no number in front of the molecule formula right here, like in front of C3H8, it's the number 1. What this tells me is 1 mole of C3H8 makes 4 moles of water. 1 mole of C3H8 makes 4 moles of water. And that's where I get the 1 mole of C3H8 makes 4 moles of water. These are exact numbers. This crosses off. I'm left with the right units. 3 significant figures, exact numbers, and you'd get 16.5 moles of water. Now, we also have the other reactant, oxygen, and we have 18.4 moles of oxygen, and we want to make how many moles of water? Again, you have your ratio, and whatever you're trying to get to goes on top of the ratio, moles of water. Whatever we're trying to get rid of goes underneath, moles of O2. Where do we get these numbers? From the balanced chemical equation. Remember, the coefficients tell you molar relationships. And for this, for every 5 moles of O2, we make 4 moles of water. So for every 5 moles of O2, we make 4 moles of water. These are exact numbers for a significant figure. Do the math. Your answer is pretty significant. You get 14.7. And the correct answer to find out how many moles of water is the lower of these two numbers, 14.7, and that's your answer. Wow, that's how you do it. And that's the information for test one. Remember, you have Saturday, this Saturday, and next Monday, Tuesday, and Wednesday to take test number one. And then Thursday, I'll pick them up and grade them. And by Saturday, I hope to have the grades posted in Blackboard. Now, because one student has to take it a little later, I will not send out the individual points until next Tuesday. And next Tuesday afternoon, 6:30, I'll send out an email. I'll go through test number one answers. So with that, I'm done. I'm going to stick around for a little while. If any of the students who are here have any questions, I'll stick around. If not, you know what I'm going to do next. I'm going to say "Gang gesund," which means go in health in Yiddish. And I'll say also, bye now. Bye. Stole that from Granny and the Beverly Hillbillies. Bye.